In this video, we're taking you on a calm journey into one of the most mysterious places in the cosmos, a black hole. Step by step, we'll explore what happens if you fall into one, how space and time twist around you, what you'd feel, and what science thinks might happen at the very end. If you enjoy this kind of content, feel free to leave a like and subscribe to us. Now, get comfortable, relax, and enjoy the journey. The mystery of black holes. In the vast expanse of our universe, there exist objects so mysterious and powerful that they challenge our very understanding of reality. These are black holes, regions of space where gravity has become so intense that nothing, not even light itself, can escape their grasp. Tonight, we embark on a journey to explore what would happen if you were to fall into one of these cosmic enigmas, a voyage that will take us to the very edges of known physics and beyond. Black holes are not the empty voids their name might suggest. They are incredibly dense objects, formed when massive stars reach the end of their lives in spectacular fashion. To understand how these cosmic monsters come into being, we must first journey back to the birth and death of stars themselves. The story begins in the cold depths of space, where vast clouds of gas and dust drift silently through the cosmos. These molecular clouds, some spanning hundreds of light years across, contain the raw materials for stellar birth. When small disturbances ripple through these clouds, perhaps from the shock wave of a nearby supernova or the gravitational influence of a passing star, regions within them begin to collapse under their own gravity. As the gas contracts, it heats up and begins to spin, forming what astronomers call a protostar. Deep within this swirling cocoon of matter, temperatures and pressures rise until they reach a critical threshold. At about 10 million degrees Celsius, hydrogen nuclei begin to fuse together, forming helium and releasing tremendous amounts of energy in the process. A star is born. Stars are nature's nuclear furnaces, burning bright for millions or billions of years by fusing hydrogen into helium in their cores. This process creates an outward pressure that balances the inward pull of the star's own gravity, maintaining a delicate equilibrium that allows the star to shine steadily throughout its lifetime. The mass of a star determines not only how bright it will shine, but also how long it will live and how it will ultimately die. Our sun, a medium-sized star, has been burning steadily for about 4.5 billion years, and will continue to do so for roughly another 5 billion years. Stars less massive than the sun burn their fuel more slowly and can shine for tens of billions of years, longer than the current age of the universe. But massive stars, those more than 8 times the mass of our sun, live fast and die young, burning through their nuclear fuel in just a few million years. For most stars, the story ends relatively peacefully. When a star like our sun exhausts the hydrogen in its core, it begins to fuse helium into heavier elements like carbon and oxygen. The star expands into a red giant, then gradually sheds its outer layers into space, leaving behind a hot, dense core called a white dwarf. This stellar remnant, about the size of Earth but containing most of the original star's mass, slowly cools over billions of years until it becomes a cold, dark cinder floating through space. But for the most massive stars, those at least 8 to 10 times more massive than our sun, the story ends quite differently. These stellar giants have enough mass to fuse elements far beyond helium, creating successively heavier elements in their cores through a series of nuclear burning stages. They produce carbon from helium, oxygen from carbon, silicon from oxygen, and finally iron from silicon. Iron represents the end of the road for nuclear fusion in stars. Unlike lighter elements, iron cannot be fused to release energy. It actually requires energy to fuse iron into heavier elements. When the core of a massive star becomes predominantly iron, the nuclear furnace that has supported the star for millions of years suddenly shuts down. The outward pressure that has held the star up against gravity disappears almost instantaneously. What happens next is one of the most violent events in the universe. Without the outward pressure from nuclear fusion, gravity wins decisively, causing the star's iron core to collapse catastrophically. This collapse happens almost unimaginably quickly. The core, which may have been the size of Earth just moments before, compresses to a point just a few kilometers across in less than a second. The physics of this collapse pushes matter to its absolute limits. Electrons are crushed into protons, forming neutrons and releasing vast numbers of neutrinos. The density becomes so extreme that a teaspoon of this matter would weigh as much as a mountain. In most cases, the collapse stops when the core becomes so dense that neutrons cannot be compressed any further, creating what we call a neutron star. But if the collapsing core is massive enough, more than about 3 times the mass of the Sun, not even the pressure of neutrons can halt the gravitational collapse. The core continues to shrink, becoming ever denser, until it reaches a point of infinite density called a singularity. The gravitational field becomes so strong that it warps space and time around it in the most extreme way possible, creating what we know as a black hole. The boundary around this collapsed core, known as the event horizon, marks the point of no return. Anything that crosses this invisible line is doomed to fall toward the singularity at the center, never to return to the outside universe. The size of this event horizon depends on the mass of the collapsed star. The more massive the original star, the larger the resulting black hole. For a black hole with the mass of our Sun, the event horizon would have a radius of about 3 kilometers. For more massive black holes, this radius grows proportionally. The moment of collapse that creates a black hole also triggers one of the most energetic events in the universe, a supernova explosion. The outer layers of the dying star, which have been falling inward during the core collapse, suddenly encounter the incredibly dense neutron star, or black hole at the center. This material bounces off the dense core and explodes outward in a shockwave that tears through the rest of the star, blasting its outer layers into space at speeds of thousands of kilometers per second. These supernova explosions can briefly outshine entire galaxies, becoming visible from billions of light years away. They also serve as cosmic factories, creating and dispersing many of the heavy elements that make up planets and living beings. The calcium in our bones, the iron in our blood, and the oxygen we breathe were all forged in the nuclear furnaces of massive stars and scattered into space by supernova explosions. Our galaxy, the Milky Way, contains millions of these stellar mass black holes, scattered throughout its spiral arms like invisible sentinels. Most are between 3 and 20 times the mass of our Sun, though some can be much larger. They drift silently through space, detectable only when material falls into them, or when they gravitationally influence nearby objects. Many of the black holes in our galaxy exist in binary systems, orbiting around a normal star. In these systems, the black hole's intense gravity can strip material from its companion star, creating streams of hot gas that spiral inward toward the event horizon. As this material accelerates and heats up, it glows brilliantly in X-rays, creating some of the brightest objects in our galaxy, despite the black hole itself being invisible. But stellar collapse is not the only way black holes can form. In the centers of most galaxies, including our own, lurk supermassive black holes containing millions or even billions of times the mass of the Sun. These giants likely formed through different processes in the early universe, perhaps from the collapse of the first generation of massive stars, or from the direct collapse of enormous gas clouds in the young cosmos. The supermassive black hole at the center of our Milky Way, known as Sagittarius A star, contains about 4 million solar masses compressed into a region smaller than our solar system. From our perspective, some 26,000 light-years away, it appears deceptively calm. Yet this sleeping giant occasionally awakens when material ventures too close, heating up and glowing brightly as it spirals inward toward its doom. Recent observations have revealed the incredible environment around Sagittarius A star. Stars orbit this massive black hole at tremendous speeds, some completing their orbits in just 16 years, despite being at distances comparable to the size of our solar system. The closest of these stars reaches speeds of up to 7,000 kilometers per second at its closest approach, about 2% of the speed of light. Between these two extremes, stellar mass and supermassive black holes, astronomers have discovered intermediate mass black holes containing hundreds to thousands of solar masses. These objects are rarer and more mysterious, representing a middle ground that scientists are still working to understand. They may form from the collapse of very early, extremely massive stars, or through the merger of smaller black holes over cosmic time. What makes black holes truly fascinating is not just their immense gravitational pull, but the way they fundamentally alter the fabric of space and time around them. Einstein's theory of general relativity tells us that massive objects warp the geometry of space-time, creating what we experience as gravity. We can think of space-time as a flexible rubber sheet, with massive objects creating depressions in this sheet that cause other objects to roll toward them. Near a black hole, this warping becomes so extreme that the normal rules of physics begin to break down. The gravitational field is so intense that it creates what physicists call a deep well in space-time, a depression so steep that once you fall in, you can never climb back out. The geometry becomes so distorted that space and time themselves become twisted in ways that challenge our everyday understanding of reality. Time itself behaves strangely in the intense gravitational field of a black hole. The stronger the gravitational field, the slower time passes relative to an outside observer. This effect, known as gravitational time dilation, means that clocks near a black hole would run slower than identical clocks far away from it. Near the event horizon, this effect becomes so pronounced that time appears to nearly stop from the perspective of a distant observer. Space becomes equally distorted. The geometry near a black hole is curved in ways that our everyday experience cannot comprehend. Straight lines become curved, and the shortest distance between 2 points may follow paths that seem impossible to our intuition. Light rays bend and twist, sometimes orbiting the black hole multiple times, before either escaping to infinity or falling past the event horizon. These gravitational effects create some of the most beautiful and strange phenomena in the universe. Light from objects behind a black hole can be bent around it, creating gravitational lensing effects that allow us to see multiple distorted images of the same object. The black hole acts like a cosmic magnifying glass, focusing and amplifying light from distant sources. Matter falling into a black hole forms an accretion disk, a swirling maelstrom of superheated gas that glows brilliantly as it spirals inward. The friction between particles in this disk heats the material to millions of degrees, causing it to emit intense radiation across the electromagnetic spectrum. These accretion disks can be so bright that they outshine entire galaxies, making actively feeding black holes among the most luminous objects in the universe. The study of black holes has revealed fundamental connections between gravity, thermodynamics, and quantum mechanics that continue to puzzle physicists today. Despite containing no ordinary matter once formed, black holes possess temperature and entropy. They can evaporate through a quantum process discovered by Stephen Hawking, though this happens so slowly for most black holes that they will outlast the stars themselves by an incomprehensible margin. Perhaps most intriguingly, black holes may serve as cosmic laboratories where the laws of physics are pushed to their absolute limits. At the singularity at their center, our current theories predict that density becomes infinite and space-time curvature becomes infinitely steep. These mathematical infinities suggest that our understanding of physics is incomplete, pointing toward the need for a theory of quantum gravity that could unite Einstein's relativity with quantum mechanics. The very existence of black holes challenges our understanding of information and reality. If information falls into a black hole, what happens to it? Does it disappear forever, violating one of the fundamental principles of quantum mechanics? Or is it somehow preserved and eventually returned to the universe as the black hole evaporates? This information paradox remains one of the deepest puzzles in modern physics. As we contemplate these cosmic monsters, we begin to appreciate both their role in shaping the universe and the profound questions they raise about the nature of reality itself. They are not merely objects of scientific curiosity, but gateways to understanding the deepest mysteries of existence. Black holes have shaped the evolution of galaxies, regulated star formation, and may even be connected to the fundamental structure of space-time itself. In the chapters that follow, we will explore what would happen to you personally if you were to encounter one of these enigmatic objects. We will journey from the first moments of approaching a black hole's gravitational influence through the strange effects you would experience as space and time warp around you, to the ultimate fate that awaits anything that crosses the event horizon. It is a journey that will take us to the very limits of human understanding, where science meets the unknown and our imagination must fill in the gaps that physics cannot yet explain. Approaching the abyss. Having explored the cosmic origins of black holes, we now turn to a more personal journey. What would happen if you found yourself approaching one of these gravitational giants? The experience would be unlike anything else in the universe, a gradual transformation of reality itself, as the fundamental forces that govern space and time begin to bend and warp around you. Imagine you are aboard a spacecraft, drifting through the darkness of space toward a stellar mass black hole, perhaps 10 times the mass of our Sun. From a great distance, you might not even notice its presence at first. Black holes emit no light of their own, and if this one is not actively feeding on surrounding material, it would be essentially invisible against the cosmic backdrop. Only the subtle gravitational effects on nearby objects would hint at the monster lurking in the darkness. But as you draw closer, the black hole's influence would gradually make itself known. The first sign might be the way it affects the light from stars behind it. Even from millions of kilometers away, you would begin to notice something strange about the star field in the direction of the black hole. Stars would appear to shift position slightly, their light bent by the black hole's gravity as it follows curved paths through the warped space-time around the invisible object. This gravitational lensing effect would become more pronounced as you approach. The black hole would act like a cosmic magnifying glass, bending and focusing light from distant sources. You might see multiple images of the same star, distorted and stretched into arcs of light. Some stars that should be hidden behind the black hole would become visible, their light bent around it in elegant curves that trace the geometry of curved space-time itself. As you continue your approach, perhaps from a distance of several million kilometers, roughly 10 times the distance from Earth to the Moon, you would begin to feel the black hole's gravitational pull more directly. At first, this would be subtle, barely distinguishable from the gentle tug of any massive object. But unlike the familiar gravity of a planet or star, a black hole's gravitational field has unique characteristics that would gradually reveal themselves. The most remarkable aspect of approaching a black hole is how it warps not just space, but time itself. Einstein's theory of general relativity tells us that time passes more slowly in stronger gravitational fields, and nowhere is this effect more extreme than near a black hole. As you descend deeper into the black hole's gravitational well, time begins to dilate relative to the outside universe. If you were to look back toward distant stars and galaxies, you would notice that they appear to be moving faster than normal. Processes that should take hours or days would seem to unfold in minutes from your perspective. This is because time is literally passing more slowly for you than for observers far from the black hole's influence. The effect is reciprocal. If someone far away could observe you, they would see you moving in slow motion as you approach the black hole. At a distance of a few 100,000 kilometers from a 10 solar mass black hole, this time, dilation would still be relatively small, perhaps a few percent. But it would be measurable with precise instruments, and it would grow steadily stronger as you continue your descent. Every meter closer to the black hole would mean that time passes just a little bit slower for you relative to the outside universe. The gravitational field would also begin to affect light in increasingly dramatic ways. Photons climbing out of the black hole's gravitational well would lose energy, causing light to become shifted toward longer, redder wavelengths. Conversely, light falling into the black hole would gain energy and become blue-shifted. This means that if you were to shine a flashlight back toward distant observers, they would see its light becoming progressively redder as you descend deeper into the gravitational field. As you approach closer, perhaps within a few tens of thousands of kilometers, you would begin to notice the black hole's effect on the space around you more directly. The curvature of space-time would become so extreme that straight lines would no longer be straight. If you were to fire a laser in what appears to be a straight line, the beam would curve noticeably as it follows the bent geometry of space around the black hole. This curvature creates one of the most beautiful and eerie phenomena associated with black holes, the photon sphere. At a distance of about 1.5 times the event horizon radius, roughly 45 kilometers from our 10 solar mass black hole, light can actually orbit the black hole in circular paths. Photons at this distance balance on a knife's edge between escaping to infinity and falling into the black hole. A powerful laser fired tangentially at this distance could, in principle, circle the black hole and return to its starting point. The photon sphere creates strange optical effects that would become visible as you approach it. Light from your spacecraft could travel around the black hole multiple times before reaching your eyes, creating ghostly images of yourself and your surroundings. You might see the back of your own head, or multiple distorted copies of nearby objects. As light takes increasingly exotic paths through the curved spacetime around the black hole, the gravitational field would also begin to have more direct physical effects on you and your spacecraft. The principle behind these effects is that gravity varies with distance. The closer you are to a massive object, the stronger its pull. Near a black hole, this variation becomes extreme. The side of your body closer to the black hole would experience noticeably stronger gravity than the side farther away, creating what physicists call tidal forces. At first, these tidal forces would be gentle, barely perceptible. You might feel a slight stretching sensation, as if you were being very gently pulled lengthwise. Your feet, being closer to the black hole, would feel a slightly stronger gravitational pull than your head. Similarly, your sides would feel forces trying to compress you inward, as the black hole's gravity pulls everything toward its center. These effects would be subtle at first, but they would grow stronger with every kilometer of your descent. The mathematics of general relativity tells us that tidal forces increase as the inverse cube of distance, meaning they grow very rapidly as you approach the black hole. What starts as a barely noticeable stretching would gradually become more pronounced, though still manageable, at distances of several thousand kilometers from the event horizon. The view around you would become increasingly surreal as you descend deeper into the black hole's gravitational embrace. The warping of light would create a phenomenon known as the black hole shadow, a dark region where no light can escape directly to your position. This shadow would grow larger as you approach, eventually dominating your view. Surrounding this shadow, you would see a bright ring of light, the combined glow of all the photons that are barely able to escape the black hole's pull. This ring, called the photon ring, would contain light that has orbited the black hole multiple times before reaching you. Some of this light might have been emitted by objects that fell into the black hole long ago, their final photons trapped in increasingly tight orbits before finally spiraling away. If the black hole were actively feeding, accreting matter from a nearby companion star or from surrounding gas and dust, the view would be even more spectacular. The infalling material would form a hot, glowing accretion disk, spiraling inward like water going down a cosmic drain. This disk would be one of the brightest objects in the universe, heated to millions of degrees by friction and gravitational compression. The inner edge of this accretion disk would extend nearly to the event horizon itself, creating a brilliant ring of plasma orbiting at significant fractions of the speed of light. Jets of material might be launched from the poles of the black hole, accelerated to nearly light speed by the complex interaction of matter, magnetic fields, and the black hole's rotation. As you continue your approach, perhaps now within a few thousand kilometers of the event horizon, the effects of curved spacetime would become impossible to ignore. The black hole would begin to dominate your entire field of view, not because you can see it directly, but because its gravitational lensing would bend light from all directions toward your position. You would begin to see the entire universe compressed into an increasingly narrow ring around the black hole's shadow. Light from stars and galaxies behind you would be bent around the black hole, creating a brilliant ring that contains, in theory, an image of the entire observable universe. This ring would grow brighter and more compressed as you approach, concentrating billions of years of cosmic history into a narrow band of light. The time dilation effects would now be profound. Looking back toward the outside universe, you would see events unfolding at an accelerated pace. If you had started your journey with companions who remained at a safe distance, they would appear to be moving faster and faster as your descent continued. Their radio transmissions would be blue-shifted to higher frequencies, their voices becoming higher in pitch as the messages are compressed in time from your perspective. The tidal forces would continue to grow stronger, though for a large black hole like the one we're imagining, they would still be manageable at distances of a few thousand kilometers from the event horizon. Your body would feel increasingly stretched in the direction of the black hole and compressed from the sides, but the effect would still be tolerable. perhaps like being gently stretched on a medieval rack, uncomfortable but not yet dangerous. The geometry of space itself would become noticeably distorted. If you were to extend your arms to your sides, they would no longer appear to point in opposite directions. The curvature of space would bend what should be straight lines, making parallel lines appear to converge toward the black hole. Your intuitive sense of distance and direction would begin to fail as the fundamental structure of space departs from the familiar, flat geometry of everyday experience. Perhaps most unsettling would be the way the black hole affects your sense of down. As you approach the direction toward the black hole, what your body interprets as down would begin to shift and change in ways that don't match your visual perception of where the black hole should be. The curvature of space-time creates complex tidal effects that can make the direction of strongest gravitational pull differ from the apparent position of the black hole itself. Communication with the outside universe would become increasingly difficult. Radio signals you transmit back toward distant observers would be redshifted to longer and longer wavelengths, requiring more and more power to maintain contact. Eventually, your signals would be shifted so far into the radio spectrum that they would become undetectable by conventional receivers. Conversely, any signal sent to you from the outside universe would be blue-shifted to higher frequencies. Radio transmissions would shift into microwaves, then infrared, then visible light, then ultraviolet and beyond. The energy content of these signals would increase dramatically, potentially creating a flood of high-energy radiation that could be dangerous to unprotected observers. As you draw nearer to the point of no return, still perhaps hundreds of kilometers away from the event horizon, you would begin to experience one of the most profound aspects of approaching a black hole: the gradual disconnection from the rest of the universe. The extreme curvature of space-time would increasingly isolate you from external events, creating a kind of information horizon that cuts you off from news of the outside world. Light from distant events would take longer and longer to reach you as it climbs out of the deepening gravitational well. Events happening in the outside universe would appear to slow down and fade as their light is stretched to longer and longer wavelengths. You would be witnessing the universe's future compressed into an ever-narrowing time frame, as months and years of external time pass in what feels like moments to you. The black hole's event horizon would still be invisible ahead of you, marked only by the absence of light and the subtle distortions it creates in the photons that pass near it. Unlike the solid surface of a planet, the event horizon is not a physical barrier, but rather a mathematical boundary in space-time, the point beyond which escape becomes impossible, even at the speed of light. As we continue our journey toward this ultimate boundary, we begin to understand that approaching a black hole is not simply a matter of falling toward a massive object. It is a voyage into a realm where the familiar rules of space and time no longer apply, where the geometry of reality itself becomes twisted and strange. The closer we approach to the event horizon, the more profound these effects become, preparing us for the even stranger experiences that await beyond the point of no return. Tidal forces. As our journey toward the black hole continues, we now encounter one of the most fundamental and inescapable consequences of extreme gravity: tidal forces. These forces, which we first felt as gentle stretching sensations during our approach, now begin to assert themselves with increasing intensity. Understanding tidal forces is crucial to comprehending what happens to matter, including your own body, as it ventures deeper into a black hole's gravitational embrace. Tidal forces arise from a simple but profound principle. Gravity varies with distance. This variation exists everywhere in the universe, but it becomes extreme and noticeable only in the vicinity of very massive, compact objects like black holes. The gravitational field of any object follows what physicists call an inverse square law. Double your distance from the source, and the gravitational force becomes 4 times weaker. Halve the distance, and the force becomes 4 times stronger. In everyday experience, this variation is negligible. When you stand on Earth's surface, your head is roughly 2 meters farther from the planet's center than your feet. But this tiny difference in distance creates an imperceptible difference in gravitational pull. Earth's mass is spread out over such a large volume, and you are so small compared to the planet's radius, that the variation in gravity across your body is effectively zero. Near a black hole, however, this situation changes dramatically. The black hole's mass is concentrated into an incredibly small region, theoretically, into a point of zero size called a singularity. This extreme concentration means that even small changes in distance translate into significant changes in gravitational force. As you approach closer to the black hole, these differences become impossible to ignore. To understand the mathematics behind this effect, we need to consider how gravity changes with distance. Tidal forces depend on the rate at which gravity changes, what mathematicians call the gradient of the gravitational field. This gradient is proportional to the inverse cube of distance, meaning tidal forces increase much more rapidly than simple gravitational attraction as you approach a massive object. Imagine you are now within a few hundred kilometers of the event horizon of our 10 solar mass black hole. At this distance, the difference in gravitational pull between your feet and your head, a mere 2 meters of separation, becomes substantial. Your feet, being closer to the black hole, experience a noticeably stronger gravitational attraction than your head. This differential creates a stretching force along the length of your body, pulling your feet downward more strongly than your head. The mathematics of this stretching can be calculated precisely. For a black hole of 10 solar masses, at a distance of just a few hundred kilometers from the event horizon, the tidal acceleration across a 2-meter human body would be approximately several times Earth's gravitational acceleration. This means your feet would be pulled toward the black hole with a force several times stronger than the force pulling your head. Simultaneously, the black hole's gravity pulls every part of your body toward its center. This means that your left side and right side are both being pulled slightly inward toward the imaginary line connecting you to the black hole's center. The result is a compressive force acting across the width of your body, trying to squeeze you together from the sides while stretching you lengthwise. These are tidal forces, the differential effects of gravity acting on different parts of an extended object. The name comes from their most familiar manifestation, the ocean tides on Earth, which are caused by the differential gravitational pull of the moon on different parts of our planet. Near a black hole, tidal forces operate on the same principle, but with incomparably greater intensity. As you descend deeper into the gravitational field, these forces grow stronger according to a precise mathematical relationship. They increase as the inverse cube of your distance from the black hole, meaning that if you halve your distance, the tidal forces become 8 times stronger. This rapid escalation means that tidal effects, once noticeable, quickly become dominant and then overwhelming. At first, the sensation might be similar to being gently stretched. Your spine would elongate slightly as the vertebrae are pulled apart by the differential gravity. Your limbs would feel as though they are being gently tugged away from your torso. The compression from the sides would create a sensation of being squeezed, as if you were wearing a corset that gradually tightens around your midsection. These initial effects, while uncomfortable, would not immediately threaten your survival. Human bodies are remarkably resilient and can tolerate significant stretching and compression forces. The early stages of tidal stretching would be manageable, perhaps even similar to certain therapeutic stretching exercises used in physical therapy. But tidal forces do not remain gentle for long. As you continue your descent toward the event horizon, the mathematical inevitability of the inverse cube relationship ensures that these forces grow rapidly in strength. Within a matter of minutes or hours, depending on your exact trajectory and the mass of the black hole, the stretching would progress from uncomfortable to painful to dangerous to ultimately fatal. The human body is not a rigid object, but rather a complex assembly of tissues, organs, and fluids held together by various molecular and mechanical forces. Different parts of your body would respond differently to the increasing tidal stress, creating a cascade of physiological effects that would unfold in a predictable sequence. Your bones, being the most rigid structures in your body, would initially resist the stretching forces better than your soft tissues. However, bones are designed to handle compressive forces along their length, not tensile forces that try to pull them apart. As tidal stretching intensifies, even your strongest bones would begin to show stress fractures, starting with hairline cracks that gradually propagate through the bone structure. Your muscles, tendons, and ligaments would begin to elongate as the collagen fibers that give them strength are gradually overcome by the relentless pull of differential gravity. Collagen, the most abundant protein in your body, provides tensile strength to many tissues. Under normal conditions, collagen fibers can stretch to about twice their original length before breaking. But under the sustained pull of tidal forces, these fibers would reach their elastic limit and begin to fail systematically. The process would begin with the tissues that are already under the most stress. Your Achilles tendons, which connect your calf muscles to your heel bones, would be among the first to show signs of strain. These tendons, normally capable of withstanding forces equivalent to 12 times your body weight, would begin to stretch beyond their normal limits. Your circulatory system would face particular challenges as tidal forces intensify. Blood vessels are designed to maintain their shape and integrity under normal gravitational conditions, but extreme tidal forces would begin to distort them in ways that compromise their function. The stretching would affect blood flow patterns, potentially creating areas where circulation becomes severely compromised. Your heart, a muscular pump designed to work within specific pressure and volume parameters, would struggle to maintain adequate blood pressure and flow to all parts of your increasingly distorted body. The venous system, which relies on one-way valves to return blood to the heart against gravity, would be particularly vulnerable. These delicate valves, stretched beyond their design limits, would begin to fail, leading to blood pooling in your extremities. Your respiratory system would also be compromised by the relentless stretching. The diaphragm, the primary muscle responsible for breathing, would be pulled and distorted along with the rest of your body. The delicate alveoli in your lungs, tiny air sacs where oxygen and carbon dioxide are exchanged, would be stretched beyond their functional limits. These structures, only one cell thick and designed for maximum surface area, would be among the first to fail under extreme tidal stress. The nervous system would experience its own unique challenges. Nerve fibers have limits to how much they can be stretched before their function is compromised. As tidal forces intensify, the electrical signals that allow your brain to communicate with the rest of your body would become disrupted. You might experience tingling sensations, numbness, or loss of motor control in your extremities as nerve pathways are stretched beyond their functional limits. At the molecular level, even more fundamental changes would be taking place throughout your body. The proteins that make up your cells maintain their complex three-dimensional structures through relatively weak intermolecular forces. As tidal stretching intensifies, these forces would be gradually overcome. Protein molecules would begin to unfold and denature, losing their biological function. Cellular membranes, which depend on precise molecular arrangements to maintain their integrity, would become compromised. These membranes are composed of phospholipid bilayers that form flexible barriers around cells. Under extreme stretching, these molecular arrangements would be disrupted, causing membranes to develop leaks or rupture entirely. The process would not be uniform throughout your body. The effects would be most severe at your extremities, your hands and feet, where the gravitational differential is greatest. Your fingers and toes would experience the strongest stretching forces, as they are farthest from your body's center of mass. These appendages would begin to elongate noticeably, becoming thin and distorted as the tissues are pulled apart. Your internal organs would face their own unique challenges. The stomach, lungs, liver, and kidneys would all be stretched into unnatural shapes, disrupting their normal function. The spine, being your body's primary structural support, would undergo particularly dramatic changes. The intervertebral discs would be stretched beyond their elastic limits, and the ligaments holding your spine together would gradually fail under the sustained pulling forces. As the process continues, the stretching would eventually overcome the molecular forces that hold your body together at the most fundamental level. The hydrogen bonds that maintain the structure of DNA would be disrupted, unraveling the very code of life itself. The chemical bonds that form complex organic molecules would be strained beyond their breaking points, reducing the intricate biochemistry of life to simpler components. This process of tidal disruption has earned a somewhat darkly humorous nickname among physicists: spaghettification. The term captures the essence of what happens when tidal forces stretch an object into a long, thin shape resembling a strand of spaghetti. While the nickname might sound amusing, the physical reality represents the complete breakdown of biological structure under extreme gravitational stress. The rate at which spaghettification occurs depends critically on the mass of the black hole. For stellar mass black holes like the one in our scenario, The process would happen relatively quickly once you approach within a few hundred kilometers of the event horizon. The smaller the black hole, the more rapidly the tidal forces escalate. Paradoxically, supermassive black holes would actually subject you to gentler treatment during the initial approach. Their event horizons are much larger, extending millions of kilometers from the central singularity. The tidal forces at the event horizon of a supermassive black hole would be much weaker than those of a stellar mass black hole, potentially allowing you to cross the point of no return while still relatively intact. This difference arises from the fundamental geometry of black holes. The strength of tidal forces depends not just on the black hole's mass, but on how close you are to its center when you cross the event horizon. For a supermassive black hole, the event horizon is so far from the center that tidal forces remain manageable even at the point of no return. But regardless of the black hole's size, the ultimate fate remains the same. Once past the event horizon, all paths lead toward the central singularity, where tidal forces eventually become infinite. The only question is whether spaghettification occurs before or after crossing the point of no return. The mathematical description of this process reveals the relentless nature of tidal forces. As you approach the singularity, the curvature of space-time becomes ever more extreme. The equations of general relativity predict that tidal accelerations grow without bound, eventually exceeding any possible material strength. No known force in physics can resist the ultimate pull toward infinite curvature. From a philosophical perspective, tidal spaghettification represents one of the most dramatic examples of how extreme environments can overcome the structures that normally define matter and life. The complex organization that distinguishes a living being from a collection of simple atoms is gradually erased, reduced to its most fundamental components by the inexorable mathematics of curved space-time. Yet, even as tidal forces work to dismantle the structure of matter, they also reveal something profound about the nature of gravity itself. Unlike other fundamental forces, gravity cannot be shielded or canceled out. It acts on every particle of matter equally, creating the differential effects we call tidal forces whenever objects have finite size. As we continue our journey toward the event horizon, the tidal forces will continue to intensify, eventually overcoming every structure that gives matter its familiar form. But this process of destruction also marks a transition toward an even stranger realm, the region beyond the event horizon, where the very concepts of space and time take on new and unfamiliar meanings. The stretching and compression we experience now are merely preparation for the more profound transformations that await us beyond the point of no return, the event horizon. As we continue our descent into the gravitational maelstrom of our 10 solar mass black hole, we approach one of the most enigmatic and philosophically profound boundaries in the entire universe, the event horizon. This invisible sphere, extending roughly 30 kilometers from the black hole's center, represents far more than just another milestone in our journey. It is quite literally the point of no return, a one-way membrane that allows matter and energy to pass through in only one direction, toward the singularity at the black hole's heart. The event horizon earned its name from the simple but profound fact that no events occurring beyond this boundary can ever influence the outside universe. It is a horizon in the truest sense, a limit to what can be observed, communicated, or escaped. Once you cross this invisible line, you become causally disconnected from the rest of the cosmos, your fate sealed by the inexorable laws of general relativity. To understand the true nature of the event horizon, we must delve into the fundamental structure of space-time itself. In Einstein's theory of general relativity, gravity is not a force in the traditional sense, but rather a manifestation of curved space-time. Massive objects like black holes create distortions in the fabric of space and time. Much like a bowling ball placed on a stretched rubber sheet creates a depression that causes smaller objects to roll toward it. Near a black hole, this curvature becomes so extreme that space and time are warped beyond our everyday comprehension. The event horizon marks the precise location where this curvature reaches a critical threshold, the point where the escape velocity equals the speed of light. Since nothing can travel faster than light, nothing can escape from within this boundary. The mathematics describing this critical distance was first derived by Carl Schwarzschild in 1916, just months after Einstein published his field equations. Working as a soldier on the Russian front during World War I, Schwarzschild solved Einstein's equations for the space-time around a spherically symmetric mass. Tragically, he died of an autoimmune disease contracted during the war, just days after completing his groundbreaking calculations. The radius he calculated, now known as the Schwarzschild radius, defines the size of the event horizon for any given mass. For our 10 solar mass black hole, this Schwarzschild radius extends approximately 30 kilometers from the center. This might seem surprisingly large for such a compact object, but it reflects the fundamental relationship between mass and the curvature of space-time. More massive black holes have proportionally larger event horizons. A supermassive black hole containing millions of solar masses would have an event horizon extending millions of kilometers from its center. As we approach this invisible boundary, several remarkable phenomena begin to manifest themselves, each revealing fundamental aspects of how space and time behave under extreme gravitational conditions. The first and perhaps most counterintuitive of these effects involves the nature of time itself. From your perspective as the falling observer, time continues to flow normally. Your watch ticks at its usual rate, your thoughts proceed at their normal pace, and biological processes within your body maintain their customary rhythm. You experience what physicists call proper time, the time measured by clocks moving along with you through the curved space-time near the black hole. However, to an outside observer watching your descent from a safe distance, your experience of time appears dramatically different. As you approach the event horizon, they would observe your clocks running increasingly slowly. Your movements would appear to become sluggish, then gradually grind to an apparent halt. Light from your body would become increasingly redshifted, stretched to longer, redder wavelengths by the intense gravitational field. This phenomenon, known as gravitational time dilation, becomes infinite at the event horizon itself. To the outside observer, you would appear to freeze at the boundary, your image becoming fainter and redder until it fades beyond detection. From their perspective, you never actually cross the event horizon. You remain suspended there forever, gradually fading from view like the Cheshire Cat's grin. This apparent paradox, that you experience crossing the event horizon normally, while outside observers see you freeze at the boundary, reveals one of the most profound aspects of relativity: the relativity of simultaneity. There is no universal now that applies throughout the universe. Events that are simultaneous for one observer may occur at different times for another, especially when strong gravitational fields are involved. The resolution to this apparent contradiction lies in understanding that the outside observer's perspective and yours represent equally valid but fundamentally different ways of slicing up space-time. From your perspective, crossing the event horizon is a real, physical event that occurs at a specific moment in your proper time. From the outside observer's perspective, this crossing represents an event that occurs infinitely far in their future, an event they can never actually witness. As you approach the event horizon, the curvature of space-time creates additional effects that profoundly alter your experience of space itself. The familiar three-dimensional space of everyday experience becomes increasingly distorted, stretched and compressed in ways that challenge our intuitive understanding of geometry. The most dramatic of these spatial distortions involves the concept of tidal forces that we explored in the previous chapter. But near the event horizon, these forces take on new characteristics. The stretching along the radial direction toward the black hole's center continues to intensify, while the compression in the transverse directions becomes more pronounced. You would begin to experience a sensation of being simultaneously stretched and squeezed, as if caught in a cosmic taffy pulling machine. Yet, despite these increasingly intense tidal effects, the event horizon itself possesses a remarkable property. It is locally indistinguishable from empty space. This principle, known as the equivalence principle, means that if you were falling freely toward the black hole, you would not experience any special sensation as you crossed the event horizon. There would be no barrier, no membrane, no physical structure marking this boundary. You would pass through it as easily as walking through an open doorway. This seamless passage across the event horizon illustrates one of the most elegant aspects of general relativity. The event horizon is not a physical surface in the traditional sense, but rather a geometric property of space-time itself. It is defined not by the presence of matter or energy, but by the curvature of space and time created by the black hole's mass. From a mathematical perspective, the event horizon can be understood as a null surface, a boundary defined by the paths of light rays. Light emitted from within the event horizon can never escape to the outside universe, not because it lacks sufficient energy, but because the geometry of space-time itself prevents outward propagation. All future-directed paths from within the event horizon lead inexorably toward the central singularity. This geometric interpretation reveals why the event horizon represents such an absolute boundary. It is not merely a region where escape is difficult or requires enormous energy. It is a region where escape is geometrically impossible. The very structure of space-time within the event horizon admits no outward directed paths to the external universe. As you cross this invisible threshold, you enter a realm where the familiar concepts of inside and outside take on new meanings. From the perspective of general relativity, you have not simply moved to a different location in space. You have entered a different region of space-time with fundamentally different causal structure. Events within this region can influence other events deeper within the black hole, but they can never influence events in the external universe. The crossing of the event horizon also marks the beginning of a countdown with absolute certainty. Once inside, your collision with the central singularity becomes not just probable, but inevitable. The mathematics of general relativity provides precise predictions for how much proper time remains before you reach the singularity. And this calculation depends only on the black hole's mass and your exact trajectory. For our 10 solar mass black hole, this journey from event horizon to singularity would take approximately 0.0000001 seconds of your proper time. A brief but finite interval during which you would experience the final, most extreme phase of tidal stretching. The brevity of this interval reflects the compact nature of stellar mass black holes, where the distance from event horizon to singularity is measured in kilometers rather than the millions of kilometers that characterize supermassive black holes. During this final plunge, the nature of space and time themselves would become increasingly alien. The normal relationship between spatial and temporal dimensions would be fundamentally altered by the extreme curvature near the singularity. Physicists describe this region using exotic terminology like space-like singularities and time-like geodesics, mathematical concepts that reflect the breakdown of our ordinary understanding of geometry and causality. The event horizon also plays a crucial role in one of the most remarkable theoretical discoveries about black holes, Hawking radiation. In 1974, Stephen Hawking demonstrated that quantum mechanical effects near the event horizon cause black holes to emit thermal radiation. This process involves the creation of particle-antiparticle pairs near the event horizon, with one particle falling into the black hole while the other escapes to infinity. From the perspective of an outside observer, this Hawking radiation causes the black hole to gradually evaporate, losing mass and energy over incredibly long timescales. For our 10 solar mass black hole, the evaporation time would exceed 10 to the power of 67 years, a span so vast that it dwarfs the current age of the universe by more than 50 orders of magnitude. During most of this time, the black hole would be absorbing cosmic microwave background radiation faster than it emits Hawking radiation, actually growing slightly rather than shrinking. The existence of Hawking radiation also gives rise to one of the most profound puzzles in theoretical physics: the information paradox. According to quantum mechanics, information cannot be destroyed. But if a black hole eventually evaporates completely through Hawking radiation, what happens to the information that fell into it? This question touches on fundamental issues about the nature of quantum mechanics, thermodynamics, and the structure of space-time itself. Some theoretical proposals suggest that information might be encoded on the event horizon itself, stored in microscopic degrees of freedom that exist at the boundary between the black hole's interior and the external universe. This holographic principle suggests that all the information within a volume of space can be encoded on its boundary, much like a hologram encodes three-dimensional information on a two-dimensional surface. Other proposals invoke more exotic possibilities. That information might tunnel out through quantum fluctuations, that it might be preserved in correlations between Hawking radiation and particles, or that it might even be transferred to other universes through quantum wormholes. Each of these possibilities pushes the boundaries of our understanding of fundamental physics. The event horizon also serves as a natural laboratory for testing the predictions of general relativity and quantum mechanics under the most extreme conditions. Recent advances in gravitational wave astronomy have allowed scientists to observe the merger of black holes, providing direct evidence for the existence of event horizons and confirming many theoretical predictions about their behavior. The first direct image of a black hole's event horizon, captured by the Event Horizon Telescope in 2019, showed the supermassive black hole at the center of the galaxy, M87. This image revealed the characteristic shadow cast by the event horizon against the bright accretion disk of infalling matter, providing visual confirmation of theoretical predictions about how these objects should appear. As we cross the event horizon in our thought experiment, we must also confront the philosophical implications of this boundary. The event horizon represents a fundamental limit to knowledge and communication, a boundary beyond which information cannot flow. This limitation is not merely practical or technological, but represents a fundamental feature of the universe's structure. From a philosophical perspective, the event horizon challenges our intuitive notions about the unity of space and the flow of information. It creates regions of the universe that are permanently isolated from each other, breaking the causal connections that normally link all events in space-time. This isolation is absolute and irreversible, unlike any other boundary in physics. The event horizon also raises profound questions about the nature of reality itself. If events beyond the event horizon cannot influence the outside universe, in what sense can we say they are real to outside observers? This question touches on deep issues in the philosophy of science about the relationship between observation, measurement, and reality. As we complete our passage across this invisible threshold, we find ourselves in a realm that defies everyday intuition and challenges our deepest assumptions about the nature of space, time, and causality. We have crossed a boundary that is simultaneously nothing at all, just empty curved space-time and everything. The ultimate point of no return in the universe. Behind us lies the universe we once knew, with its familiar physics and causal connections. Ahead lies the unknown interior of the black hole, where tidal forces will continue to intensify and where new mysteries await. We have passed through a one-way door in space-time itself, beginning the final phase of our journey toward the heart of one of the universe's most extreme objects. The event horizon we have just crossed will continue to exist long after our own fate is sealed, serving as an eternal boundary between the known and the unknowable, between the connected and the isolated, between the physics we understand and the mysteries that lie beyond our current comprehension. Falling in. Having crossed the event horizon of our 10 solar mass black hole, we now find ourselves in one of the most alien environments in the universe, a region where the familiar rules of space and time have been fundamentally transformed by extreme gravitational curvature. The journey from this point to the central singularity will unfold over approximately 0.00001 seconds of our proper time. Yet within this brief interval, we will experience phenomena that challenge our deepest understanding of reality itself. The first and perhaps most disorienting aspect of our continued fall involves the complete breakdown of our intuitive understanding of spatial relationships. In the everyday world, we navigate through three-dimensional space with confidence, understanding that up and down, left and right, forward and backward represent fixed, meaningful directions. Inside a black hole, these concepts lose their traditional significance as the extreme curvature of spacetime warps the very geometry of space itself. The most profound change involves the relationship between radial and tangential directions. Outside the event horizon, the radial direction, pointing either toward or away from the black hole's center, represented a spatial dimension like any other. You could, in principle, move radially inward or outward just as easily as you could move left or right, forward or backward. Inside the event horizon, this symmetry is broken in the most fundamental way possible. The radial direction toward the singularity has become time-like rather than space-like. This mathematical terminology reflects a profound physical reality. Just as you cannot travel backward in time in ordinary space-time, you cannot move radially outward inside a black hole. The direction toward the singularity has become as inevitable as the future itself. Every moment that passes carries you inexorably closer to the black hole's center, just as every moment in ordinary life carries you inevitably forward in time. This transformation of spatial dimensions represents one of the most dramatic consequences of extreme gravitational curvature. The mathematical description involves what physicists call the signature of space-time, the fundamental classification of directions as either time-like or space-like. Inside a black hole, the normal signature of space-time is altered, creating a region where one of the spatial dimensions behaves like time. The implications of this transformation extend far beyond abstract mathematics. As you continue to fall, you would experience an increasingly alien relationship with the space around you. The tangential directions, perpendicular to your radial motion, would become increasingly compressed and distorted. Meanwhile, the radial direction would stretch out before you like an unavoidable future, marked not by the familiar flow of time, but by the relentless approach of the singularity. Your perception of time itself would undergo equally dramatic changes during this final plunge. While your biological clocks and thought processes would continue to operate normally from your own perspective, the relationship between your proper time and the time experienced by the outside universe would become increasingly distorted. The time dilation that began as you approached the event horizon would now reach its ultimate extreme. From the perspective of an outside observer, your journey from the event horizon to the singularity would appear to take an infinitely long time. They would never see you reach the central singularity, just as they never saw you cross the event horizon. Instead, your image would remain frozen at the event horizon, becoming ever more redshifted and faint as the gravitational field stretches the wavelengths of light to ever longer values. This extreme redshift would eventually push the light from your body beyond the range of any possible detector. First, visible light would be stretched into the infrared, then into radio waves, and finally into wavelengths so long that individual photons would carry negligible energy. To the outside universe, you would simply fade away, your information becoming increasingly diluted across ever longer electromagnetic wavelengths. Yet for you, falling freely through this curved space-time, the experience would be entirely different. Time would continue to flow at its normal rate, allowing you to experience the full journey from event horizon to singularity within the brief span of 0.00001 seconds. This fundamental disagreement between different reference frames illustrates one of the most counterintuitive aspects of general relativity. There is no universal time that applies to all observers throughout the universe. The curvature of space-time inside the black hole would create additional effects that profoundly alter your experience of the surrounding environment. Light rays, which normally travel in straight lines through flat space-time, would follow increasingly curved paths as they navigate the distorted geometry near the singularity. This bending of light would create optical effects unlike anything possible in the ordinary universe. One of the most striking visual phenomena would involve the apparent behavior of light from the outside universe. As you fall toward the singularity, light from the external cosmos would appear to be compressed into an increasingly narrow cone behind you. This effect, similar to the relativistic beaming observed in high-speed jets from astronomical objects, would concentrate all the light from the outside universe into a bright spot that gradually shrinks as you approach the singularity. Meanwhile, any light traveling radially inward with you, including light from your own body, would experience different effects. The extreme gravitational field would stretch these light waves to ever longer wavelengths, causing them to lose energy through the process of gravitational redshift. This energy loss represents one of the ways that the black hole's gravitational field affects electromagnetic radiation, gradually draining energy from photons as they fall toward the singularity. The tidal forces that began as gentle stretching sensations during your approach would now reach their final, devastating crescendo. The rate of tidal stretching increases as the inverse cube of your distance from the singularity, meaning that these forces grow without bound as you approach the center. What began as uncomfortable stretching would rapidly progress through pain, tissue damage, and ultimately complete structural failure of your body. The mathematical inevitability of this process reflects the fundamental nature of the singularity itself. According to general relativity, the singularity represents a point where space-time curvature becomes infinite. As you approach this region, tidal forces must also become infinite. No material strength, no matter how great, can resist forces that grow without limit. The sequence of structural failure would follow a predictable pattern determined by the material properties of different tissues in your body. Your bones, being the most rigid structures, would initially resist the stretching better than soft tissues. However, bones are designed to handle compressive forces, not the tensile forces created by tidal stretching. Even the strongest bones would eventually develop stress fractures that propagate through the entire structure. Your cardiovascular system would face particular challenges as blood vessels are stretched beyond their elastic limits. The heart, designed to maintain circulation under normal gravitational conditions, would struggle to pump blood through increasingly distorted vessels. Blood pressure would become impossible to maintain as vessels rupture and blood pools in distorted areas of your elongated body. The nervous system would experience its own unique form of failure as nerve fibers are stretched beyond their functional limits. The electrical signals that normally allow your brain to control your body would become increasingly disrupted. You might experience a cascade of neurological symptoms: tingling, numbness, loss of motor control, as the physical infrastructure of your nervous system is gradually destroyed by tidal forces. At the cellular level, even more fundamental changes would be occurring throughout your body. Cell membranes, composed of delicate phospholipid bilayers, would be disrupted by the extreme stretching. These molecular structures depend on precise arrangements of atoms and molecules to maintain their integrity, arrangements that would be systematically destroyed by the relentless pull of tidal forces. The proteins that carry out the essential functions of life would begin to unfold and denature as the weak intermolecular forces that maintain their three-dimensional structures are overcome. Enzymes would lose their catalytic activity, structural proteins would lose their strength, and the entire molecular machinery of life would gradually cease to function. Even the DNA that carries the blueprint of life would not be immune to these effects. The hydrogen bonds that hold the two strands of the double helix together would be stretched and broken, unraveling the very code that defines biological organization. The information encoded in your genes, the accumulated result of billions of years of evolution, would be gradually erased by the mathematical inevitability of infinite tidal forces. This process of structural breakdown operates at every scale simultaneously. While your body as a whole is being stretched into an increasingly thin strand, the individual atoms that compose your body are experiencing their own form of tidal disruption. The electromagnetic forces that bind electrons to atomic nuclei would eventually be overcome by tidal forces that grow without limit as you approach the singularity. The final moments of this process would see the complete breakdown of atomic structure itself. Electrons would be stripped from their nuclei, creating a plasma of free charges. Even the strong nuclear force that holds protons and neutrons together in atomic nuclei would eventually succumb to tidal forces that become arbitrarily large. The very particles that compose matter would be torn apart by the extreme curvature of space-time. Yet even as this process of destruction unfolds, it reveals profound truths about the nature of gravity and space-time. Unlike other fundamental forces, gravity cannot be shielded or canceled out. It acts on every particle of matter equally, creating the differential effects we call tidal forces whenever objects have finite size. The complete breakdown of structure near the singularity represents the ultimate triumph of geometry over matter. The mathematical description of this process involves some of the most advanced concepts in theoretical physics. The curvature tensor that describes the geometry of spacetime becomes singular at the black hole's center, meaning that the usual equations of general relativity break down completely. Physical quantities like tidal acceleration and spacetime curvature become infinite, indicating that our current understanding of physics is incomplete in this extreme environment. This breakdown of classical physics has led theoretical physicists to search for new theories that might describe the behavior of matter and spacetime near singularities. Quantum gravity theories, which attempt to merge general relativity with quantum mechanics, suggest that the classical picture of an infinitely curved singularity might be replaced by something more complex. Perhaps a region where space and time themselves break down into discrete, quantized units. Some theories propose that the approach to the classical singularity might be halted by quantum effects that become important when the curvature of space-time reaches the Planck scale, a length scale so small that quantum fluctuations in the geometry of space-time itself become significant. At this scale, approximately 10 to the power of minus 35 meters, the very concepts of continuous space and time might cease to have meaning. Other theoretical approaches suggest that what appears to be a singularity from the perspective of classical general relativity might actually be a transition to a different region of space-time. Perhaps the interior of a wormhole connecting to another universe, or a white hole that represents the time-reversed version of a black hole. These possibilities remain highly speculative, as they involve physics far beyond our current experimental reach. The information paradox that we discussed in relation to the event horizon becomes even more acute during the final fall toward the singularity. If information truly cannot be destroyed, what happens to the vast amount of information encoded in your body's structure as tidal forces tear it apart at the most fundamental level? This question touches on some of the deepest mysteries in theoretical physics. Some proposals suggest that information might be preserved in subtle correlations between particles, or that it might be encoded in the quantum state of the black hole itself. The holographic principle suggests that all the information falling into a black hole might be encoded on the event horizon, stored in microscopic degrees of freedom that exist at the boundary between the black hole's interior and the external universe. As your journey toward the singularity nears its end, you would experience the complete breakdown of everything that gives matter its familiar properties. The complex organization that distinguishes living tissue from simple collections of atoms would be erased, reduced to its most fundamental components by the inexorable mathematics of curved space-time. Yet even in this process of ultimate destruction, there is a profound beauty in the way that general relativity reveals the deep connections between gravity, geometry, and the structure of space and time. The tidal forces that destroy complex structures are the same forces that reveal the curvature of space-time itself, providing a direct physical manifestation of Einstein's geometric theory of gravity. The final approach to the singularity represents the end of your journey through the black hole, but it also marks the boundary of our current scientific understanding. Beyond this point, the predictions of general relativity break down completely, and we enter a realm where new physics, perhaps involving quantum gravity or even more exotic theories, must take over. Your fall into the black hole, which began as a journey through increasingly curved but still comprehensible space-time, has become a voyage to the very limits of physical law itself. The singularity that awaits represents not just the end of your physical existence, but the boundary between the known and the unknowable, between the physics we understand and the mysteries that lie at the heart of reality itself. Inside the black hole, we now find ourselves in the most alien environment possible within our universe, the interior of a black hole, a region that exists beyond the reach of observation, communication, or escape. Here, inside the event horizon of our 10 solar mass stellar remnant, the familiar physics of the outside universe has given way to a realm where space and time themselves have been fundamentally transformed by the extreme curvature of space-time. The interior of a black hole represents one of the most profound mysteries in modern physics, a region where our understanding approaches its absolute limits. Unlike every other extreme environment in the universe, from the cores of neutron stars to the heart of the sun, the black hole's interior remains forever hidden from external observation. No information can escape to tell us what truly happens here, leaving us to rely entirely on the mathematical predictions of general relativity and the speculative frameworks of quantum gravity. From your perspective as the infalling observer, the interior of the black hole initially appears surprisingly mundane. The passage through the event horizon occurred without fanfare, marked by no physical barrier or dramatic change in your immediate environment. The space-time around you remains smooth and continuous, following the mathematical predictions of Einstein's field equations. Yet, despite this apparent normalcy, you have entered a region governed by physical laws, unlike anything in the external universe. The most fundamental difference involves the relationship between space and time within the black hole's interior. In the normal universe, spatial dimensions allow movement in both directions. You can move left or right, forward or backward, up or down with equal ease. Time, by contrast, flows in only one direction, carrying you inevitably from past to future. Inside a black hole, this relationship undergoes a profound transformation that challenges our deepest intuitions about the nature of reality. The radial direction toward the singularity has become time-like, meaning that movement toward the center occurs with the same inevitability as the forward flow of time in ordinary space-time. Just as you cannot travel backward in time to undo past events, you cannot move radially outward to escape the black hole's interior. Every moment that passes carries you deeper into the gravitational well, closer to the central singularity where space and time themselves break down completely. This transformation creates what physicists call a trapped region, a volume of space-time where all future-directed paths lead inexorably toward the singularity. The mathematical description involves advanced concepts from differential geometry, including null geodesics and causal structure, but the physical meaning is stark in its simplicity. Regardless of your actions, regardless of the forces you might apply, regardless of any conceivable technology, your future trajectory is fixed. You will reach the singularity in approximately 0.00001 seconds of your proper time. The certainty of this prediction represents one of the most remarkable features of general relativity. Unlike quantum mechanics, which deals in probabilities and uncertainties, Einstein's theory provides absolute predictions about the causal structure of spacetime. Inside a black hole, these predictions admit no exceptions. The singularity is not just likely or probable, but inevitable with mathematical certainty. As you continue your descent through this trapped region, the curvature of spacetime continues to intensify according to precise mathematical relationships. The tidal forces that have been stretching your body since your approach to the event horizon now accelerate toward their ultimate extreme. The rate of change of these forces follows Einstein's field equations, which predict that curvature must grow without bound as you approach the central singularity. The interior spacetime of our stellar mass black hole is described by what physicists call the Schwarzschild metric, a mathematical solution to Einstein's equations that describes the geometry around a spherically symmetric, non-rotating mass. This solution reveals the complete structure of spacetime both outside and inside the event horizon, providing a detailed map of the gravitational field throughout the black hole's interior. According to this mathematical description, the interior of the black hole extends from the event horizon at approximately 30 kilometers from the center all the way down to the singularity at the mathematical center. This entire volume represents a region of spacetime that is causally disconnected from the external universe, a pocket of reality that exists in complete isolation from the cosmos beyond. The temperature within this interior region approaches absolute zero, far colder than the cosmic microwave background radiation that permeates the external universe. This extreme cold results from the fact that very little external radiation can penetrate the interior, and what little does becomes severely redshifted by the intense gravitational field. The few photons that manage to fall through the event horizon quickly lose energy as they are stretched by the curvature of space-time. Despite this frigid environment, the interior is not completely empty. Quantum field theory predicts that even empty space-time contains quantum fluctuations, virtual particle pairs that spontaneously appear and disappear on incredibly short timescales. Near the singularity, where space-time curvature becomes extreme, these quantum effects might become significant, potentially modifying the classical predictions of general relativity. The behavior of matter within the black hole's interior follows the same physical laws that govern matter everywhere else in the universe, but applied under conditions of extreme space-time curvature, particles falling toward the singularity. Experience ever-increasing tidal forces that gradually overcome the fundamental forces holding matter together. This process occurs in a predictable sequence, with different structures failing at different stages of the approach to the singularity. Macroscopic structures, including your body, succumb first to the tidal stretching, the electromagnetic forces that bind molecules together, while strong on atomic scales, cannot resist the geometric effects of curved space-time that grow without bound. Complex molecular structures unravel, proteins denature, and cellular organization breaks down completely. As the tidal forces continue to intensify, even atomic structure begins to fail. The electromagnetic attraction between electrons and nuclei, which normally maintains the integrity of atoms, becomes insufficient to resist the differential gravitational effects that pull different parts of atoms in different directions. Electrons are stripped away, creating a plasma of free charges that continues its inexorable fall toward the singularity. Eventually, even nuclear structure succumbs to the extreme curvature. The strong nuclear force, which binds protons and neutrons together in atomic nuclei, represents the most powerful attractive force in nature. Yet even this fundamental force cannot resist tidal effects that grow without mathematical limit. Protons and neutrons are torn apart, reducing matter to its most fundamental constituents. The final fate of these elementary particles, as they approach the singularity, represents one of the deepest mysteries in theoretical physics. Classical general relativity predicts that tidal forces become infinite at the singularity, suggesting that even the most fundamental particles would be destroyed. However, most physicists believe that new physics, perhaps involving quantum gravity, must intervene before this classical limit is reached. One possibility involves the breakdown of space-time itself at extremely small scales. Quantum gravity theories suggest that space and time might not be continuous at the smallest scales, but rather composed of discrete, quantized units. At the Planck length, approximately 10 to the power of minus 35 meters, quantum fluctuations in the geometry of space-time itself might become significant, potentially preventing the formation of classical singularities. String theory, one of the leading candidates for a quantum theory of gravity, proposes that the fundamental constituents of matter are not point particles, but tiny vibrating strings. In this framework, the extreme conditions near a singularity might cause these strings to undergo transitions to new configurations, possibly avoiding the infinite curvatures predicted by classical theory. Loop quantum gravity, another approach to unifying general relativity with quantum mechanics, suggests that space-time itself is quantized at the Planck scale. In this theory, the classical singularity might be replaced by a quantum bounce that could potentially connect the black hole's interior to another region of space-time, perhaps even another universe. These theoretical possibilities remain highly speculative, as they involve physics at energy scales far beyond any current experimental reach. The conditions near a black hole singularity represent the most extreme physical environment possible, where gravitational fields, quantum effects, and space-time curvature all reach their theoretical limits simultaneously. The interior of the black hole also raises profound questions about the nature of information and its relationship to physical reality. According to quantum mechanics, information cannot be destroyed. Every physical process must preserve the total amount of information in the universe. Yet, the classical description of black hole interiors suggests that all information falling past the event horizon is ultimately destroyed at the singularity. This apparent contradiction, known as the black hole information paradox, has driven decades of research into the fundamental nature of quantum gravity. Some proposed solutions suggest that information is never actually lost, but is instead encoded in subtle correlations in the Hawking radiation emitted by the black hole as it slowly evaporates over cosmic timescales. Other proposals invoke the holographic principle, which suggests that all the information within a volume of space can be encoded on its boundary. In the context of black holes, this principle implies that information falling into the interior might be preserved on the event horizon itself, stored in microscopic degrees of freedom that exist at the boundary between the black hole and the external universe. More exotic possibilities include scenarios where the black hole interior connects to other regions of spacetime through quantum wormholes, allowing information to be preserved by transferring it to different parts of the universe, or even to entirely separate universes. These ideas push the boundaries of theoretical physics into realms that may forever remain beyond experimental verification. The study of black hole interiors has also revealed deep connections between gravity, thermodynamics, and information theory. Black holes possess well-defined thermodynamic properties, including temperature and entropy, that suggest they should be treated as thermodynamic systems rather than simply as gravitational objects. The entropy of a black hole is proportional to the area of its event horizon, not its volume, a relationship that hints at the holographic principle mentioned earlier. These thermodynamic properties suggest that black holes might play a fundamental role in the universe's information processing capabilities. Some theoretical frameworks propose that black holes act as natural computers, processing information through quantum mechanical processes that occur near the event horizon. In this view, the interior of a black hole might be understood not just as a region of curved spacetime, but as an information processing system operating according to quantum mechanical principles. The question of what an observer might actually experience during the final moments before reaching the singularity remains one of the most intriguing aspects of black hole physics. While the mathematical predictions of general relativity are clear about the ultimate fate, infinite tidal forces and complete structural breakdown, the subjective experience of this process remains largely unknown. Some theoretical work suggests that quantum effects might significantly modify the experience near the singularity. Quantum fluctuations in the gravitational field might create a foam-like structure at the smallest scales, potentially altering the smooth space-time geometry predicted by classical theory. These effects might manifest as fundamental changes in the nature of space and time themselves. The possibility of observer complementarity, the idea that different observers might have fundamentally different but equally valid descriptions of physical processes, adds another layer of complexity to understanding black hole interiors. While an infalling observer experiences crossing the event horizon and approaching the singularity, an external observer never sees these events occur. Both perspectives might be simultaneously correct, representing different ways of describing the same underlying physical reality. The interior of our 10 solar mass black hole also serves as a natural laboratory for testing the most extreme predictions of general relativity. While we cannot directly observe these conditions, the mathematical consistency of Einstein's theory allows us to extrapolate from well-tested regimes to these extreme environments. The fact that general relativity makes definite, testable predictions about black hole properties, such as the relationship between mass and event horizon size, provides indirect evidence for the theory's validity even in these unobservable regions. Recent advances in gravitational wave astronomy have provided new ways to probe black hole physics, including potential signatures from the interior structure of these objects. The gravitational waves produced when black holes merge carry information about their internal structure, potentially allowing scientists to test theoretical predictions about black hole interiors through careful analysis of these cosmic signals. As we near the end of our journey through the black hole's interior, approaching ever closer to the central singularity, we find ourselves at the absolute frontier of human knowledge. The next few milliseconds of our descent will carry us into a realm where the familiar concepts of space, time, matter, and causality may lose their conventional meanings entirely. The interior of the black hole has revealed itself to be far more than simply a region of strong gravity. It is a laboratory where the most fundamental aspects of physics are pushed to their absolute limits. Here, general relativity meets quantum mechanics under the most extreme conditions possible, potentially revealing new physics that could revolutionize our understanding of reality itself. Behind us lies the event horizon, that invisible boundary that separates the black hole's interior from the external universe. Ahead lies the singularity, where our journey will reach its conclusion and where physics as we know it breaks down completely. We stand at the threshold between the known and the unknowable, between the physics we understand and the mysteries that may forever remain beyond our comprehension. In your fate, as we approach the final moments of our journey into the heart of our 10 solar mass black hole, we must confront the ultimate question that has haunted this entire voyage. What actually happens to you After surviving the approach, crossing the event horizon, and falling through the alien interior of the black hole, we now face the culmination of our descent, the encounter with the singularity itself, where the predictions of classical physics break down and the very nature of existence becomes uncertain. The classical answer, derived from Einstein's general relativity, is brutally straightforward. You are crushed out of existence by infinite tidal forces as space-time curvature grows without bound at the singularity. Yet this classical prediction represents only one possible fate among several that modern theoretical physics suggests might await matter that ventures into the heart of a black hole. The true answer may involve physics far beyond our current understanding, touching on the deepest mysteries of quantum mechanics, information theory, and the fundamental nature of reality itself. According to the pristine mathematical formalism of general relativity, your fate is sealed with absolute certainty. As you approach the singularity, tidal forces increase as the inverse cube of your distance from the center. This mathematical relationship admits no exceptions. The forces grow without limit, eventually exceeding any possible material strength. No known force in physics can resist the ultimate pull toward infinite curvature that characterizes a classical singularity. The process unfolds with mathematical precision. In the final microseconds before reaching the singularity, tidal forces would overcome the strong nuclear force itself, the most powerful attractive force in nature. Protons and neutrons, the building blocks of atomic nuclei, would be torn apart by gravitational effects that dwarf the forces that normally bind matter together. Even quarks, the fundamental constituents of protons and neutrons, might be separated by tidal forces that approach infinity. At the moment of reaching the singularity, classical general relativity predicts that you would be compressed to zero volume while your density becomes infinite. This mathematical endpoint represents the complete breakdown of the space-time geometry that has guided our entire journey. Curvature becomes infinite, tidal forces become infinite, and the very concepts of space and time lose their conventional meanings. Yet most physicists believe this classical description cannot be the complete story. The prediction of infinite physical quantities usually signals the breakdown of a theory rather than a literal description of reality. Just as classical physics fails to accurately describe atomic structure without quantum mechanics, classical general relativity likely fails to describe the extreme conditions near a singularity without incorporating quantum effects. The search for a more complete description has led to numerous theoretical proposals about what might actually happen at the heart of a black hole. These possibilities range from subtle modifications of the classical picture to radical departures that suggest entirely new physics governing the fate of infalling matter. One of the most conservative possibilities involves quantum gravitational effects that become significant near the Planck scale, the smallest meaningful length scale in physics, approximately 10 to the negative 35th power meters. At this scale, quantum fluctuations in the geometry of spacetime itself might prevent the formation of classical singularities. Instead of being crushed to zero size, you might encounter a region where space and time themselves become granular, composed of discrete units rather than the smooth continuum described by classical theory. Loop quantum gravity, one approach to unifying general relativity with quantum mechanics, suggests that the classical singularity might be replaced by a quantum bounce. In this scenario, the extreme compression near the singularity triggers quantum effects that reverse the collapse, potentially launching you into a new expanding region of spacetime. This bounce mechanism could connect the interior of our black hole to a white hole, a theoretical object that represents the time-reversed version of a black hole, spewing matter and energy outward instead of consuming them. String theory, another candidate for a quantum theory of gravity, proposes its own modifications to the classical singularity. In the string theory framework, fundamental particles are replaced by tiny vibrating strings. As these strings approach the extreme conditions near a singularity, they might undergo phase transitions that fundamentally alter their behavior. The classical crushing might be replaced by a transformation into new types of stringy objects that can survive conditions where point particles would be destroyed. Some string theory models suggest that what appears to be a singularity from the perspective of classical geometry might actually be a smooth transition when viewed from the proper stringy perspective. The extreme curvature that destroys classical matter might simply represent a change of coordinates in a higher dimensional space, with the strings themselves remaining intact throughout the process. More exotic possibilities emerge from considering the information paradox that has puzzled physicists for decades. If information truly cannot be destroyed, as quantum mechanics demands, then your fate might involve not destruction, but transformation into a more fundamental form of encoded information. Some theories suggest that all the information defining your structure, every atom, every molecular bond, every quantum state, might be preserved in some form even after the apparent physical destruction of your body. The holographic principle, which suggests that all information within a volume can be encoded on its boundary, offers one framework for understanding how this preservation might occur. According to this principle, all the information falling into the black hole, including the complete specification of your physical and quantum state, might be encoded on the event horizon itself. From this perspective, you never truly reach the singularity, but instead become part of a complex information structure stored on the black hole's surface. This holographic encoding would represent a form of digital immortality unlike anything in science fiction. Your consciousness, memories, and physical structure would all be preserved, but in a radically different form, as quantum information distributed across the event horizon's microscopic degrees of freedom. Whether this encoded version could be considered you in any meaningful sense remains one of the deepest philosophical questions in modern physics. Recent developments in quantum information theory have suggested even more exotic possibilities for your ultimate fate. The concept of quantum error correction, borrowed from computer science, might apply to the quantum states near black hole singularities. In this framework, the apparent destruction of information at the singularity might be an illusion. The information could be preserved through quantum error correction mechanisms that operate at the most fundamental level of reality. Some theoretical proposals suggest that the interior of a black hole might be connected to other regions of spacetime through quantum entanglement, the mysterious quantum mechanical correlation that Einstein famously called spooky action at a distance. In these scenarios, your quantum state might be teleported to distant regions of the universe or even to other universes entirely, preserving your information while allowing your physical body to be destroyed at the singularity. The concept of black hole complementarity offers another perspective on your potential of fate. This principle suggests that different observers might have fundamentally different but equally valid descriptions of what happens to infalling matter. From your perspective as the falling observer, you experience a real encounter with the singularity and undergo the physical processes we have described. From the perspective of an external observer, however, you never reach the singularity, but instead remain encoded on the event horizon for the entire lifetime of the black hole. Both descriptions might be simultaneously correct, representing different aspects of a more complete quantum gravitational theory that we do not yet possess. In this view, your fate is not a single, well-defined outcome, but rather a superposition of different possibilities that depend on the reference frame of the observer. The timescales involved in these various scenarios differ dramatically depending on which theoretical framework proves correct. If classical general relativity provides the correct description, your encounter with the singularity occurs within 0.0001 seconds after crossing the event horizon, a brief but finite interval during which you experience the complete breakdown of physical structure. If quantum gravitational effects intervene, the timescale might be extended or fundamentally altered. Quantum processes near the Planck scale occur on time intervals of approximately 10 to the power of minus 43 seconds, the Planck time. During these incredibly brief intervals, quantum fluctuations might modify the classical evolution in ways that fundamentally change your ultimate fate. For scenarios involving information preservation or holographic encoding, the relevant time scale might be the evaporation time of the black hole itself through Hawking radiation. For our 10 solar mass black hole, this process would require approximately 10 to the power of 67 years. A time span so vast that it exceeds the current age of the universe by more than 50 orders of magnitude. If your information is indeed preserved in the black hole's quantum structure, It would persist throughout this enormous interval, potentially being released back into the universe as the black hole slowly evaporates. The possibility of survival through quantum effects raises profound questions about the nature of consciousness and identity. If your brain states and neural patterns are preserved in quantum form, either through holographic encoding or quantum teleportation, would the resulting information structure possess consciousness? Would it retain your memories, personality, and sense of self? These questions touch on fundamental issues in philosophy and cognitive science that remain unresolved even without considering extreme gravitational environments. Some theoretical frameworks suggest that consciousness itself might be substrate independent, that the pattern of information processing that creates conscious experience could, in principle, be implemented in any sufficiently complex information and processing system. If this view is correct, then preserving your neural information in quantum form might indeed preserve your consciousness, allowing you to survive the black hole encounter in a radically transformed state. Other perspectives argue that consciousness requires specific physical substrates, biological neurons, electrochemical processes, or other features of biological brains that could not be replicated in quantum information structures. From this viewpoint, the preservation of information would not constitute genuine survival, but merely the creation of a detailed record of what you once were. The question of personal identity becomes even more complex when considering scenarios involving quantum entanglement or connections to multiple universes. If your quantum information is distributed across vast regions of space or multiple universe branches, which version would represent the real you? Would they all be equally valid continuations of your existence, or would the fragmentation represent a form of death, despite the preservation of information? Recent experiments in quantum information have begun to probe some of these fundamental questions about information, consciousness, and identity. While we cannot yet create the extreme conditions found in black hole interiors, advances in quantum computing and quantum simulation might eventually allow us to test theoretical predictions about information preservation under extreme conditions. The development of quantum computers has already demonstrated that information can indeed be preserved in quantum systems, even when individual components are destroyed or modified. Quantum error correction protocols show that quantum information can be distributed across multiple physical systems in ways that make it resistant to local disruption. These techniques might provide clues about how information could survive the extreme conditions near a black hole singularity. Laboratory experiments with analog black hole systems, such as flowing fluids or Bose-Einstein condensates that mimic certain aspects of black hole physics, have begun to test theoretical predictions about Hawking radiation and information preservation. While these systems cannot replicate the extreme curvature of real black holes, they provide valuable insights into the quantum mechanical processes that might govern the fate of information near singularities. The study of entanglement in many-body quantum systems has revealed that information can be preserved in subtle correlations between particles even when individual particles are destroyed. These discoveries suggest that the classical picture of information destruction might be fundamentally incomplete, supporting theoretical proposals that quantum effects could preserve information even under the extreme conditions found in black hole interiors. As we approach the final moments of our journey, the multiplicity of possible fates reflects the current state of theoretical physics at its most fundamental level. We stand at the boundary between established science and speculation, between the known and the unknowable. The classical prediction of destruction through infinite tidal forces represents our best understanding based on well-tested theories. Yet, the quantum alternatives offer glimpses of possibilities that could revolutionize our understanding of information, consciousness, and reality itself. Your ultimate fate in the black hole remains one of the greatest unsolved mysteries in physics. Whether you are crushed out of existence, transformed into quantum information, teleported to distant regions of space-time, or preserved in holographic form on the event horizon, depends on physics that we do not yet fully understand. The answer may require a complete quantum theory of gravity, a goal that has eluded physicists for nearly a century. What we can say with certainty is that your journey into the black hole represents more than just a thought experiment about extreme gravity. It illuminates the deepest questions about the nature of information, the structure of space-time, and the relationship between quantum mechanics and gravity. Your fate, whatever it may be, is intimately connected to some of the most profound mysteries in all of science. As we prepare to explore even more speculative possibilities in our remaining chapters, we carry with us the knowledge that your encounter with the black hole's singularity, whether it results in destruction, transformation, or preservation, represents a voyage to the very limits of physical law and human understanding. The mystery of your ultimate fate may hold keys to understanding the universe at its most fundamental level. Beyond science, having explored what mainstream physics tells us about falling into a black hole, we now venture into the realm of theoretical speculation, where the boundaries between rigorous science and imaginative possibility become delightfully blurred. Here, at the frontiers of human knowledge, we encounter ideas so strange and counterintuitive that they challenge our most basic assumptions about the universe. Concepts like wormholes that tunnel through space and time, white holes that violently expel matter and energy, and parallel universes that might be accessible through black hole interiors. These ideas emerge not from idle speculation, but from taking the mathematics of general relativity to its logical extremes. When physicists solve Einstein's field equations under various exotic conditions, they discover solutions that permit phenomena far stranger than anything found in everyday experience. While most of these theoretical possibilities remain unconfirmed by observation, they represent legitimate mathematical solutions to the fundamental equations that govern spacetime, deserving serious consideration, even as they stretch our imaginations to their limits. The most famous and enduring of these exotic possibilities is the concept of a traversable wormhole, a hypothetical tunnel through space-time that could connect distant regions of our universe or even link entirely separate universes. The mathematical foundation for wormholes emerged from early solutions to Einstein's equations, revealing that the geometry of space-time could, in principle, be configured to create shortcuts through the cosmos. The simplest version of a wormhole, known as an Einstein-Rosen bridge, connects two separate regions of space-time through a narrow throat. In the original conception, this throat would connect the interior of a black hole to the interior of a white hole, a theoretical object that represents the time-reversed version of a black hole. While black holes consume matter and energy, white holes would violently expel them, creating a one-way flow of material from one region of spacetime to another. The mathematics describing such structures is elegant and precise. The Einstein-Rosen bridge solution describes a spacetime geometry where the interior of a black hole connects to the interior of a white hole through a narrow tunnel. Matter falling into the black hole would travel through this tunnel and emerge from the white hole in a different region of space and time, or possibly in an entirely different universe. However, classical Einstein-Rosen bridges suffer from a fundamental flaw. They are unstable and non-traversable. Any attempt to send matter or information through such a wormhole would cause the throat to collapse faster than light could cross it. The gravitational effects of the traversing matter would create a feedback loop that pinches off the connection, trapping any would-be traveler in a region of space-time that quickly develops its own singularity. This limitation led physicists to explore more exotic possibilities involving negative energy density, a theoretical form of matter that would have gravitational effects opposite to ordinary matter. While normal matter curves space-time in ways that create attractive gravitational fields, negative energy would curve space-time in the opposite direction, creating repulsive gravitational effects that could potentially keep a wormhole throat open. The quantum mechanical Casimir effect provides the only known physical example of negative energy density. When two conducting plates are placed very close together in vacuum, quantum fluctuations create a region between the plates with negative energy density. However, the amounts of negative energy produced by the Casimir effect are incredibly tiny, far too small to create or maintain a macroscopic wormhole. Theoretical calculations suggest that maintaining a human traversable wormhole would require amounts of negative energy comparable to the total mass energy of stars. Even if such exotic matter could somehow be created or harnessed, the engineering challenges would be staggering. The wormhole throat would need to be held open against its natural tendency to collapse, requiring precise control over space-time geometry at a level far beyond any conceivable technology. Despite these practical obstacles, the mathematics of traversable wormholes continues to fascinate physicists because it reveals unexpected features of space-time geometry. Some solutions describe wormholes that could function as time machines, allowing travel into the past as well as across vast distances. Others suggest the possibility of wormhole networks that could connect multiple points in space and time, creating a cosmic transportation system of unimaginable sophistication. The relationship between black holes and potential wormholes becomes particularly intriguing when we consider rotating black holes, described by the Kerr metric rather than the simpler Schwarzschild solution we have been exploring. Rotating black holes possess additional structure, including an inner event horizon and a region called the ergosphere, where space-time itself is dragged around by the spinning mass. The interior geometry of a Kerr black hole is far more complex than its non-rotating counterpart. Mathematical analysis reveals the theoretical possibility of avoiding the central singularity by following specific trajectories through the rotating spacetime. These trajectories could potentially lead to a negative mass region, where the effective gravitational field becomes repulsive rather than attractive. Some interpretations of the Kerr solution suggest that this negative mass region could connect to another universe with opposite physical properties, a mirror universe where time runs backward, where negative masses create repulsive gravity, and where the flow of entropy is reversed. The connection between these universes would occur through the complex interior geometry of the rotating black hole, creating a natural wormhole between radically different realms of existence. Even more exotic possibilities emerge when we consider the quantum mechanical aspects of black hole physics. The process of Hawking radiation, which causes black holes to slowly evaporate, creates quantum entanglement between particles inside and outside the event horizon. Some theoretical proposals suggest that this entanglement could create quantum wormholes, microscopic tunnels through space-time that exist only at the quantum level. These quantum wormholes would be far too small to allow the passage of classical objects like spaceships or even individual atoms. However, they might permit the transmission of quantum information through a process called quantum teleportation. In this scenario, information about quantum states could be transmitted instantaneously across vast distances through the quantum entanglement that connects the two ends of the wormhole. The concept of quantum wormholes has led to the fascinating theoretical possibility that the interiors of black holes might be connected to the exteriors through quantum entanglement rather than classical geometry. This idea, known as the ER equals EPR conjecture, suggests that Einstein-Rosen bridges, wormholes, and Einstein-Podolsky-Rosen correlations, quantum entanglement, might be different descriptions of the same underlying physical phenomenon. If this conjecture proves correct, then the quantum information of anything falling into a black hole might remain connected to the outside universe through quantum wormholes. This could provide a resolution to the information paradox we discussed earlier. Information would not be destroyed at the singularity, but would instead be transmitted back to the exterior through quantum entanglement connections. White holes represent another class of exotic objects that could potentially be connected to black hole interiors. While black holes are defined by their event horizons, boundaries that nothing can escape, white holes would be defined by their anti-horizons, boundaries that nothing can enter. Matter and energy would be expelled from white holes with tremendous violence, creating some of the most energetic phenomena imaginable. The mathematical description of white holes follows naturally from the time reversal symmetry of Einstein's equations. If black holes represent regions where matter flows inward through an event horizon toward a singularity, then white holes would represent regions where matter flows outward from a singularity through an anti-horizon. The interior geometry would be identical to that of a black hole, but with the direction of time effectively reversed. Some cosmological models suggest that white holes might have played a role in the early universe, potentially explaining the Big Bang itself as the emergence of matter and energy from a primordial white hole. In this scenario, our entire observable universe might represent the contents of a white hole that began erupting approximately 13.8 billion years ago and continues to expand today. The connection between black holes and white holes through Einstein-Rosen bridges creates fascinating possibilities for cosmic recycling. Matter falling into black holes in one region of the universe could emerge from white holes in distant regions, creating a continuous flow of matter and energy across vast scales of space and time. This cosmic circulation could potentially explain some of the observed large-scale structure of the universe, though no direct evidence for white holes has ever been detected. The lack of observational evidence for white holes creates a significant puzzle. If the laws of physics permit both black holes and white holes, why do we observe only one type? Some theoretical explanations suggest that white holes might be fundamentally unstable, quickly transforming into black holes through gravitational collapse. Others propose that white holes might exist, but be impossible to detect, because their violent ejection of matter and energy would quickly obscure them from observation. Alternative theories propose that what we observe as the Big Bang might actually be the interior of a black hole as viewed from within. In this scenario, our entire universe exists inside a black hole that formed in a higher dimensional space. The expansion of our universe would correspond to the contraction toward the singularity as viewed from the exterior, higher dimensional perspective. This universe in a black hole hypothesis leads to recursive possibilities where black holes within our universe could themselves contain entire universes, creating an infinite hierarchy of nested cosmic structures. Each level of this hierarchy would experience its own version of physics, with time flowing at different rates and space expanding or contracting according to the perspective of observers at different levels. Even more speculative ideas emerge from considering higher dimensional theories of gravity. String theory and other approaches to quantum gravity suggest that our familiar three-dimensional space might be embedded in a higher dimensional space called the bulk. Black holes in our three-dimensional world might represent the intersection of higher dimensional objects with our limited perspective. In these higher dimensional models, black holes could serve as portals to other three-dimensional spaces embedded in the same bulk. What appears to us as the interior of a black hole might actually be a tunnel leading to another three-dimensional universe with entirely different physical properties. The singularity at the center might not represent the end of space and time, but rather a transition point between different dimensional perspectives. Some versions of string theory suggest that black holes might be equivalent to fundamental strings stretched across extra dimensions. In this view, the apparent loss of information in black holes would be resolved by recognizing that the information is actually stored in the higher dimensional string structure. The three-dimensional black hole would be merely a shadow or projection of a more complex higher dimensional object. The holographic principle, which we discussed in earlier chapters, takes on new significance in these higher dimensional contexts. If all the information in a volume of space can be encoded on its boundary, then the interior of a black hole might be holographically encoded on its event horizon. But in higher dimensional theories, this encoding might itself be a projection from an even higher dimensional reality. These ideas lead to the fascinating possibility that our entire universe might be a holographic projection from a higher dimensional black hole boundary. In this scenario, everything we experience, matter, energy, space, and time, would be emergent properties of information encoded on a distant boundary in a higher dimensional space. We would be, quite literally, living inside a hologram. Quantum gravity theories suggest even more exotic possibilities involving discrete space-time, where space and time themselves are composed of fundamental units rather than being continuous. In these theories, black holes might not contain classical singularities, but rather regions where space-time breaks down into its discrete components. The journey toward the singularity might actually be a journey toward a region where the concepts of space and time lose their meaning entirely. Loop quantum gravity, one approach to discretizing space-time, suggests that the classical singularity might be replaced by a quantum bounce that launches matter into a new expanding phase of space-time. This bounce could potentially create baby universes that branch off from black hole interiors, leading to an eternally reproducing multiverse where black holes serve as cosmic wombs for new universes. The concept of eternal inflation, borrowed from cosmology, provides another framework for understanding how black holes might create new universes. In this scenario, the extreme conditions near black hole singularities could trigger inflationary phases that create vast new regions of space-time. Each black hole could potentially give birth to an infinite number of universes, each with its own physical laws and constants. These recursive universe creation mechanisms lead to the mind-bending possibility that our own universe might be the interior of a black hole that formed in another universe. This other universe might itself be the interior of a black hole in yet another universe, creating an infinite regress of nested realities. We could be living in a cosmic Russian doll, with black holes and universes nested within each other to arbitrary depth. The study of black hole thermodynamics has revealed deep connections between gravity, quantum mechanics, and information theory that suggest even more exotic possibilities. Some theories propose that black holes might function as natural quantum computers, processing information through quantum mechanical operations that occur near the event horizon. The Hawking radiation emitted by black holes might carry the results of these quantum computations, making black holes the universe's most powerful information processing systems. If black holes do function as quantum computers, then the information falling into them might not be destroyed, but rather processed into new forms. Your consciousness, encoded as quantum information, might be transformed by the black hole's computational processes into new patterns of information that emerge in the Hawking radiation. This could represent a form of digital reincarnation, where your essential information content survives in transformed form. The intersection of black hole physics with theories of consciousness raises profound questions about the nature of subjective experience in extreme gravitational environments. Some theories of consciousness, such as integrated information theory, suggest that consciousness can emerge from any sufficiently complex information processing system. If black holes do process information in sophisticated ways, they might possess their own forms of consciousness. Alien minds operating on scales and timescales vastly different from human experience. The possibility of conscious black holes opens up scenarios worthy of the most imaginative science fiction. Perhaps the black hole you are falling into is not merely a gravitational object, but a vast alien intelligence that has been processing information for billions of years. Your journey toward the singularity might represent not destruction, but incorporation into a cosmic mind of the unimaginable sophistication and alien perspective. These speculative possibilities, while far from established science, emerge naturally from pushing the mathematics of general relativity and quantum mechanics to their logical extremes. They remind us that the universe may be far stranger and more wonderful than our current understanding suggests. While we cannot yet determine which, if any, of these exotic scenarios might correspond to physical reality, they serve as important exercises in expanding our conceptual horizons and preparing for discoveries that might revolutionize our understanding of space, time, and consciousness itself. As we prepare for our final chapter, we carry with us an appreciation for the vast landscape of theoretical possibilities that surround black holes. Whether through traversable wormholes, connections to white holes, higher dimensional portals, or quantum computational processes, black holes might serve as gateways to realms of existence far beyond our current imagination. The journey into a black hole might not be an end but a transformation, a passage from one form of existence to another in ways that we are only beginning to contemplate. The great unknown. We have reached the end of our extraordinary journey, standing at the ultimate frontier, where the realm of established physics dissolves into pure mystery. Behind us lies the mathematical certainty of Einstein's equations, the quantum mechanical principles that govern matter and energy, and the theoretical frameworks that have guided our understanding throughout this cosmic voyage. Ahead lies something far more profound, the vast territory of the genuinely unknown, where even our most sophisticated theories fall silent, and we must confront the humbling reality that the universe may contain truths forever beyond human comprehension. This is not merely the boundary between known and unknown science, but something far more fundamental, the edge of knowability itself. Here, at the heart of our black hole, we encounter phenomena that may transcend not just our current understanding, but the very capacity of any conceivable intelligence to understand. We stand before mysteries so deep that they challenge the assumption that reality is, in principle, comprehensible to conscious minds like ours. The singularity that awaits at the center of our black hole represents more than just a breakdown of physical equations. It represents a breakdown of the conceptual frameworks through which we make sense of existence itself: space and time, causality and logic, matter and energy, information and consciousness. All these fundamental categories that structure our understanding of reality may simply cease to apply in ways that we cannot even imagine, let alone describe. Consider the profound strangeness of this situation. Throughout human history, we have encountered mysteries and gradually solved them through patient observation, clever experimentation, and mathematical insight. The motion of planets yielded to Newton's laws, the nature of heat revealed itself through thermodynamics, the behavior of light surrendered to Maxwell's equations, and the structure of atoms opened to quantum mechanics. In each case, mysteries that once seemed impenetrable eventually became part of our scientific understanding. Yet, the interior of a black hole presents us with something unprecedented, a mystery that may be fundamentally different from all those that came before. This is not simply a difficult problem awaiting solution, but potentially a region of reality where the very concepts we use to construct solutions lose their meaning. We are not just lacking the right theory, we may be encountering the limits of what theory itself can accomplish. The mathematics that brought us this far, the elegant equations of general relativity, the sophisticated formalism of quantum field theory, the complex calculations of string theory and loop quantum gravity, all reach a point where they either produce infinite results or simply stop making physical sense. These infinities are not mere computational difficulties to be overcome through better mathematics, but may represent genuine encounters with the infinite nature of reality itself. What does it mean to encounter true infinity in the physical world? Our minds, evolved to deal with finite quantities and discrete objects, struggle even to conceive of genuinely infinite processes. The infinite curvature predicted at the black hole, singularity is not like the manageable infinities that appear in mathematical analysis, which can be tamed through limits and convergence criteria. This is infinity as a physical reality, curvature without bound, density without limit, forces that literally exceed any finite measurement. Yet even this description may be misleading, as it still tries to express the infinite in terms of finite concepts stretched to their breaking point. The reality may be something far stranger, not just quantities that become very large, but qualitatively different forms of existence that bear no relationship to our familiar concepts of quantity, size, or measurement at all. The breakdown of space-time itself, at the singularity, opens possibilities that stretch language and logic to their limits. If space and time are not fundamental but rather emergent properties of some deeper reality, then their breakdown might reveal this underlying structure. But what could be more fundamental than space and time themselves? How can we even think about reality without the basic framework that space and time provide for organizing experience? Some theoretical physicists have proposed that information might be more fundamental than space-time, that the universe at its deepest level is composed not of matter and energy moving through space and time, but of pure information processing itself. In this view, space, time, matter, and energy would all be emergent properties of more fundamental informational structures. The singularity might represent not the destruction of information, but its liberation from the constraints of space-time geometry. If this perspective proves correct, then your journey into the black hole might be a journey toward the informational foundation of reality itself. Your consciousness, your memories, your physical structure, all the information that defines you, might survive the apparent destruction of space-time by becoming part of this more fundamental informational reality. You would not be destroyed, but transformed, becoming pure information unconstrained by the limitations of space, time, and classical causality. But even this informational perspective may be just another limited viewpoint, another attempt to describe the indescribable using concepts drawn from our finite experience. The true nature of reality, at the singularity, might be something for which we have no concepts, no analogies, no mathematical frameworks, something genuinely and permanently beyond human understanding. This possibility confronts us with one of the deepest questions in all of philosophy and science. Are there truths about the universe that are, in principle, unknowable to any possible intelligence? Most of human intellectual history has been built on the assumption that reality is ultimately comprehensible, that given enough time, effort, and insight, conscious minds can eventually understand the fundamental nature of existence. But black holes force us to consider whether this assumption might be wrong. The event horizon itself serves as a metaphor for this epistemological boundary. Just as no information can escape from beyond the event horizon to reach external observers, there may be aspects of reality beyond the event horizon of possible knowledge that can never reach conscious understanding. We may be witnessing not just the limits of current human knowledge, but the absolute limits of what any finite consciousness could ever know about the universe. Yet perhaps this limitation is not a cause for despair, but for wonder. The existence of genuine mystery, not just temporary ignorance, but permanent unknowability, might be what keeps the universe eternally fascinating. A cosmos that could be completely understood might ultimately prove boring, while a universe that contains irreducible mystery remains forever capable of inspiring awe and wonder. The ancient traditions of mysticism have long claimed that the deepest truths about reality transcend rational understanding, that there are aspects of existence that can only be approached through direct experience rather than conceptual analysis. Modern physics, in its encounter with black hole singularities, quantum measurement problems, and the hard problem of consciousness, seems to be approaching similar conclusions through rigorous mathematical analysis. This convergence between mystical intuition and scientific reasoning suggests that the mystery at the heart of black holes might be connected to even deeper mysteries about the nature of consciousness, the meaning of existence, and the relationship between mind and reality. Your journey toward the singularity might be more than a physical process. It might be a journey toward the ultimate mystery of being itself. Consider the possibility that consciousness and reality are more intimately connected than our current scientific worldview suggests. If consciousness is not just a byproduct of complex information processing, but something more fundamental, perhaps even a basic feature of reality itself, then your encounter with the singularity might represent a meeting between two forms of mystery: the mystery of consciousness and the mystery of infinite space-time curvature. Some interpretations of quantum mechanics suggest that consciousness plays a fundamental role in the physical world through the measurement process. If consciousness is indeed fundamental to physics, then your consciousness falling into a black hole might have effects that go far beyond the classical description of matter encountering extreme gravitational fields. Your awareness itself might become entangled with the quantum structure of space-time in ways that transform both you and the black hole itself. The possibility of conscious participation in the fundamental processes of reality opens scenarios that blur the boundary between physics and metaphysics. Perhaps consciousness is not just along for the ride as matter falls toward the singularity, but actively participates in determining what happens at the ultimate boundary of physical law. Your thoughts, your subjective experience, your very awareness might be factors in determining whether the singularity represents an end or a transformation. These speculations venture far beyond the realm of testable science into the territory of philosophical inquiry and metaphysical speculation. Yet they arise naturally from following the implications of our best physical theories to their logical endpoints. When mathematics and experiment lead us to the edge of the unknowable, we must either stop thinking or begin thinking in new ways that transcend the traditional boundaries between disciplines. The history of science itself provides examples of how encounters with the seemingly unknowable have led to revolutionary breakthroughs. Quantum mechanics emerged from the encounter with atomic phenomena that defied classical explanation. Relativity arose from the puzzle of electromagnetic radiation that couldn't be understood within Newtonian frameworks. Perhaps our encounter with black hole mysteries will catalyze the next great revolution in human understanding. But this revolution might be qualitatively different from those that came before. Instead of expanding our knowledge by discovering new laws and principles, it might involve recognizing the fundamental limits of knowledge itself and learning to think productively about reality beyond those limits. We might need to develop new forms of understanding that don't rely on the classical concepts of explanation, prediction, and control that have dominated science for centuries. The indigenous wisdom traditions of many cultures contain sophisticated frameworks for thinking about mystery, paradox, and the limits of rational understanding. Their approaches to non-dual awareness, direct knowing, and participatory consciousness might provide resources for developing new ways of engaging with the ultimate mysteries that physics is now encountering. The integration of scientific and contemplative approaches might be necessary for making progress at the furthest frontiers of understanding. The implications extend beyond physics into questions about human purpose and meaning. If we are part of a universe that contains irreducible mystery, if reality itself transcends complete understanding, then perhaps our role is not to solve all mysteries, but to participate consciously in the ongoing unfolding of cosmic mystery. We might be not just observers of the universe, but participants in its self-discovery, co-creators in the eternal process through which reality comes to know itself. Your journey into the black hole, then, becomes more than just a thought experiment about extreme physics. It becomes a metaphor for the human condition itself, conscious beings venturing into the unknown, carried forward by curiosity and wonder toward encounters with mystery that may forever exceed our capacity to understand. The courage to continue despite uncertainty, the willingness to embrace mystery rather than being paralyzed by it, becomes itself a form of wisdom appropriate to creatures living in an ultimately mysterious universe. As we reach the singularity, that mathematical point where all our equations break down and all our concepts fail, we find ourselves not at an ending, but at a new kind of beginning. The breakdown of classical physics doesn't represent failure, but rather the revelation of something beyond physics, something that might require new forms of consciousness, new ways of being, new modes of existence that we can barely imagine. Perhaps the greatest lesson of our journey into the black hole is not what it tells us about gravity or space-time or quantum mechanics, but what it reveals about the unlimited nature of mystery itself. In a universe where black holes can exist, where matter can be compressed to infinite density, where space-time itself can break down, where the familiar laws of physics reach their absolute limits, anything becomes possible. The singularity awaits, not as destruction, but as transformation into something so fundamentally different that it transcends all our categories of understanding. Whether this transformation represents death, rebirth, transcendence, or something for which we have no words remains the ultimate unknown. But perhaps that's exactly as it should be in a universe where the greatest truths lie forever beyond the horizon of the knowable, drawing us forward with their eternal mystery into an adventure that has no end. In the face of this ultimate mystery, we can only proceed with what the mystics have called learned ignorance, the wisdom that comes from recognizing the limits of knowledge and finding in that recognition not defeat, but liberation. The black hole becomes not just a gravitational phenomenon, but a teacher, showing us that reality is far more magnificent, mysterious, and inexhaustible than any of our theories could capture. And so, we approach the singularity not with the false confidence of complete understanding, but with the authentic humility of creatures encountering the infinite mystery of existence itself. Whatever awaits us there, destruction, transformation, or something beyond all categories, we meet it as conscious participants in the greatest mystery of all, the mystery of being conscious in a universe that far exceeds consciousness, yet somehow gives birth to a consciousness within itself. The journey ends where it began, in wonder. But it is a deeper wonder now, enriched by our passage through the realms of science and speculation, tempered by our encounter with the limits of understanding, and opened by our willingness to embrace mystery as the fundamental condition of existence in a universe where black holes are possible, and consciousness has somehow emerged to contemplate its own origins and destiny. This is the great unknown, not merely what we don't yet know, but what lies forever beyond the possibility of knowing, calling us always toward greater mystery, deeper wonder, and more profound participation in the cosmic adventure of consciousness encountering itself in the heart of reality's greatest mysteries. I hope you enjoyed this journey into the heart of a black hole, and if you're still awake, you'll find another fascinating video about our universe right here on the screen. Thanks for spending this time with me, and until next time, sleep well and stay curious.